Oh man. Alright, so we are going to delve into the esoteric world of rate and concentration and identifying orders of reactants, etc. So this is pretty data heavy, and I know you guys, this has been a slog. We've been sitting at our desk looking at numbers, trying to iron these things out for quite some time, and I promise, as soon as we can get our reactant order process down, I'm going to get you guys in the lab doing some hands-on stuff. It's just a slog, and I'm sorry, but there is no replacement for grinding your way through some of these numbers, okay? But I want you to know that I'm sensitive to that. We're going to keep slogging our way through and hopefully come out the other side looking pretty good, okay? That being said, let's talk a little bit about rate and concentration. So now at this point in your science careers, right, we've already kind of made a qualitative understanding of how concentration of reactants affects the rate at which a reaction proceeds. Okay, and we can look at that in several ways. So let's say, for example, I've got a reaction container, right? And I've got a mix of various colors. So let's say I've got a whole bunch of yellow particles. And I've also got a whole bunch of blue particles. All right, so, and in this reaction, my yellow plus my blue is going to give me what color? What does yellow and blue make when I do this? It's going to give me green, right? And so what we would expect to see in this process, all right, is because my reaction container here has lots and lots of yellow and lots of blue, okay, I would expect there to be lots and lots of collisions between those particles. And so initially, at the beginning, okay, my rate of formation of green is going to be high. Okay, so there's going to be lots and lots of collisions. But what we have to understand is the more green particles I make, the fewer yellow and blue particles there are to collide. All right, and so later on in that reaction, all right, I'm going to have lots and lots of green particles. Okay, but really only a few stray yellows and a few stray blues hanging out in there, okay? And so because of that, the frequency of collisions between the yellows and blues is going to be much lower, and as a result, my rate of that reaction down the road is going to decrease. And so if I was to graph the reaction rate, for example, right? So this would be time, this would be rate, all right? So what we'd expect is initially the reaction rate to be high, all right? But then as time goes on, that reaction rate would slow down, okay, as we proceed. Okay, so if this is my rate on my y-axis here, initially a high rate, that rate's going to decrease over time, and probably go through some sort of exponential decrease. Okay, we will talk about the different types of reactants and what that slope actually looks like at a later date. But that's what we expect to see. So qualitatively, right, as our concentration of reactants goes down, our rate also goes down over time. Okay, and so I feel like at this point you guys can probably wrap your minds around that piece fairly easily, right? Our rate goes down because there's fewer collisions between the reactant particles, and that's simply because there are fewer reactant particles present to actually bump into each other. Okay? Now, quantitatively describing that relationship between the concentration of my reactants and the associated formation of my product. It's a little bit more complicated, but not too complicated. Okay, and this being a mathematical based science, right, we are going to identify that quantitative or that mathematical relationship between the concentration of our reactants and the rate at which that reaction occurs. Okay, so there's our scope, right? There's our context. Let's take a look at what I'm going to expect you guys to be able to do if given some data. All right, so we're going to talk about first, second, third, etc. order reactants. Okay, and so when we say the order of a reactant with respect to a reactant, we're referring to a mathematical relationship between the change in concentration of a reactant, which we might represent with the delta big M, change in molarity, okay, and the corresponding change in the rate, which would be delta R, okay? And so essentially, I have a reactant, all right? And the amount of that reactant is going to play some sort of role in the rate of my reaction, okay? And so what we're trying to understand with this idea of an order of a reactant is, let's say I double my reactant. What impact does that have on the rate of the reaction? Okay, that's what the order of the reactant tells you. Okay, so again, if I change my concentration of my reactant, how will that affect the rate of the overall reaction? And there are some mathematical relationships I'm going to show you guys how to identify. All right, and that's ultimately what the bulk of ChemQuest 43 is doing, is we're working through how to look at data to identify the order of your individual reactants. Okay, moving forward. Here is table 1, by the way, from ChemQuest 43. And so initially, as we go through this, we're essentially going to be covering numbers 1 through 13 from ChemQuest number 43. All right, just kind of the basic ideas of what's going on here. So here it goes. How can we determine the degree to which the concentration of each reactant affects the reaction rate? That's what we're trying to answer. And so first, we're going to look at each reactant singularly, all right? And the way we can do that is we're going to identify 2 experiments where only the reactant in question changes, okay? And then we can use this formula, high concentration over low concentration, to the n power equals the high rate over the low concentration rate. Okay? So for example, if I wanted to know how the order of the reactant with respect to chlorine dioxide, I would pick 2 experiments to compare. And the 2 experiments I would pick would be 2 in which only the concentration of the chlorine dioxide changes. So right here, it says initial ClO2, and the brackets mean molarity of, so that's referring to the actual concentration. So the initial molarity of chlorine dioxide in experiment 1 is 0.020 molarity. All right. In reaction 2, it's 0.040 molarity. So there's a change. Okay. Now, in order to compare these 2 experiments, though, the chlorine dioxide could be the only thing that changes. So now we would look at our other reactant, which is the molarity of our hydroxide ion, and we should notice the hydroxide stays the same. So if I want to know my order with respect to ClO2, I can compare reactions 1 and 2 because ClO2 changes while hydroxide stays the same. And that is the qualifying detail. To compare 2 experiments to find the order of a specific reactant, only one of the reactants may change concentration between the 2 experiments. Okay, so another place we could look, if we wanted to, we could compare reactant 2 and 6, or sorry, 1 and 6, for example, because we see a change in ClO2, but hydroxide stayed the same. So that's another option if we wanted to know the order of ClO2, okay? Because again, only the ClO2 changes while the hydroxide stays the same, okay? Now likewise, if I wanted to know the order with respect to hydroxide, I would turn the tables on that and look for 2 experiments where only the hydroxide changes and the ClO2 does not. All right? Again, that is the qualifying feature to do this. So we have to start there by picking out 2 experiments with which to compare. Okay, so when I plug in my equation here, it is this value for n, right? That exponent is what tells me the order of my reactant. So let's put this into practice. All right, so let's solve for the order with respect to chlorine dioxide. So again, we already picked out the fact that experiments 1 and 2 will work because I see a change in my molarity of ClO2, whereas those stay the same. All right, so my formula that I'm going to use is high concentration over low concentration to the nth power equals high concentration rate over low concentration rate. Okay, so what I'm going to do is my high concentration is 0.040 m over 0.020 m to the n power is going to be equal to my high concentration rate. So at my higher concentration, my rate is 0.01104 molarity per second over 0.00276 molarity per second. All right. So what I should get here, when I simplify my equation, I should get 2 to the n power equals 4. All right. So when I divide here, I should get 2. When I divide here, I should get 4. All right. So again, this value of n is my reactant order. So 2 to what power equals 4? And as we all know, n in this case would be 2. So the order with respect to ClO2 is 2. All right. So now let's turn the tables and let's find the order with respect to hydroxide. So again, I want to find 2 experiments where only the hydroxide changes. Okay, so what I can do is I can pick 2 where my initial ClO2 is the same. So 0.020 and 0.020. So where my hydroxide is 0.030 and 0.060. So in this case, I can compare experiments 1 and 3. Okay, so my high concentration is 0.060 m over 0.030 m to the n power equals 0.0552 over 0.00276, and I should get 2 to the n power equals 2, and therefore n equals 1. All right. Now, in this reaction then, I would say that the order with respect to chlorine dioxide is 2, and the order with respect to hydroxide is 1. All right. Now, what does that mean? Okay, so if n equals 2, then that means if the reactant doubles, the rate goes up 4 times, right? If n equals 1, then that means if the reactant doubles, the rate also doubles. Okay, so the n there being an exponential value, right? Whatever if n is 1, whatever the change in concentration is, we should see an equal change in our rate. If n is equal to 2, whatever our change in concentration is, we would see a change in the rate, that same amount, to the power of 2. Okay, so if n equals 2, let's say I triple my reactant, okay, then my rate would be 9 times faster. Okay, and that's the way that works. It's the change in my reactant to the power of whatever my order is. Okay, moving forward. Getting tired. Rate law. Rate law. All right. So, rate law is an equation we can use. Okay, so once we have found the order of our individual reactants, we can plug some numbers in to the rate law formula. All right, and we can solve for a value given the letter K, which is our rate constant, which has some crazy, goofy units that are not the same every time. It depends on the individual orders of reactants and so on. All right, so let's see what the rate law would look like for this reaction. So again, we've already decided that the order with respect to ClO2 is 2. And the order with respect to OH minus is 1. So those are our reactant orders. Okay? So now that we know that, all right, I can plug some numbers in right there, and I can plug another number in right there. Okay? So the way that would look for this particular reaction is the rate of my reaction would be equal to the rate constant of this reaction times the molarity of ClO2 to the second power times the molarity of hydroxide to the first power. And now notice the 2 and the 1 came from right there. Okay? And so to solve for our rate constant, in this case, all we would have to do is pick an experiment, plug in the values, and solve for K. All right? So let's put this whole thing into perspective by accomplishing number 18 from page 4 of your ChemQuest. So again, trying to value your time. All right, so start to finish, the rate law. All right, so what do we have to do in order to do rate law? I need to find the order with respect to my two reactants. Okay, so my order for H2O2. All right, so I'm going to find two experiments where this is the only thing that changes. All right, and so it changes from experiment 2 to 3, where the hydrogen iodide or hydroiodic acid stays the same. So I can pick experiments 2 and 3. So I'm going to go 0.2 over 0.1 to the n power equals 0.2432 over 0.0608. All right, and then doing my division, I should get 2 to the n power equals 4, and therefore n equals 2. So the order with respect to H2O2 is 2. I'm just going to write a little 2 up there so I remember that. All right, now my order with respect to hydrogen iodide or hydroiodic acid, okay, will be found by picking two experiments where HI is the only thing that changes. So in that case, I can pick experiments 1 and 2 because my H2O2, you notice, stays the same, whereas there is a change in my HI. Okay, so again, I'm going to take my high over low, 0.2 over 0.1 to the n power. It's going to be equal to 0.0608 over 0.2432. Whoops. Excuse me. Wrong number. 0.0076. All right. And simplifying that, I should get 2 to the n equals 8. And n would be 3 in that case. Okay. So that's a reactant order of 3 for the hydrogen iodide. Okay, so my rate law. So you guys should have notes. So my rate is going to be equal to K times the molarity of H2O2 to the second power times the molarity of HI to the third power. Okay, so there's my equation for my rate law. Now, I would like to know the rate constant, which is my value K in this case. Okay, so to solve for K, I have 3 experiments to choose from. It does not matter which one I choose, just so long as I use all the values from the same experiment. So let's just choose reactant 1, or experiment 1 in this case. I'm going to erase some of these marks. Okay, so here's my equation. So my rate for experiment 1 is 0.0076 big M over S. It's going to be equal to K, the value I don't know, times 0.1 squared times 0.1 cubed. Okay, and so simplifying this equation, I should get 0.0076 molarity per second equals K times 1.0 times 10 to the negative 5th. Okay, now here's where my units are going to get kind of goofy, and I will spend more time in class on this. But keep in mind, right, these are my molarities, right? So my units, means molarity squared and molarity cubed. So that means my units here would be molarity to the 5th power. Okay, again, kind of goofy, and I'm undecided at this moment just how stingy I am going to be on units. It does get a little confusing. Okay, so solving for K, I'm going to have to go 0.0076 molarity per second divided by 1 times 10 to the negative 5th molarity to the 5th. And therefore, K would be equal to 760. Okay. And my units would be 1 over molarity to the 4th power times seconds. Okay. So again, the unit aspect here, right? We could talk more about that if you're really, really curious. I don't know just how stingy I'm going to be on you guys as far as getting those units right, because it just adds a whole nother layer of complexity, and I don't necessarily think that's what's needed at this point. Okay, I think I think we are better off sticking with just being able to solve for our rate constant. All right, now this is a lot. This is fairly intense in practice. We're going to work our way through it slowly but surely, and I promise I'll get you guys in the lab pretty soon. Okay, but for now we just need to work hard to wrap our minds around what's going on.